types of semiconductor. Semiconductor is a material that has resistance values between that of a conductor and insulator. Examples of semiconductor materials, which are commonly used in the electronic industry, are germanium, silicon, boron, tellurium, arsenic, antimony and selenium. Germanium and silicon are commonly used semiconductor materials in the electronic industry. In semiconductor production, doping intentionally introduces impurities into an extremely pure semiconductor, for the purpose of modulating its electrical properties. The electrical conductivity of a semiconductor can be improved by adding small traces of impurities. There are two types of extrinsic semiconductors, produced by doping, that is N-type semiconductor and P-type semiconductor. Each silicon or germanium atom of a pure semiconductor has 4 electrons in the valence band to form valence bonds with 4 neighboring atoms. If atoms with 5 valence electrons or pentavalent atoms such as arsenic, antimony, or phosphorus are doped into silicon, there is an excess electron after 4 valence bonds are formed. Therefore, the excess free electrons become the negative charge carriers. Such semiconductor are known as N-type. If atom with 3 valence electron or trivalent atoms such as boron, gallium or indium are doped into silicon, there is a deficiency of 1 electron after every 4 valence bonds are formed. An electron is pulled from a neighboring atom to fill the deficiency in a valence bond, which thus become a hole. Therefore, the hole become the positive charge carriers. Such semiconductor are known as P-type. The following table shows the comparison between N-type and P-type semiconductor. N-type semiconductor is an extrinsic semiconductor, which is obtained by doping the pentavalent impurity atoms such as arsenic, antimony or phosphorus to the pure germanium or silicon semiconductor. The impurity atoms added provide extra electrons or free electron in the structure and are called donor atom. The electrons are majority charges carriers and holes are minority charge carriers. P-type semiconductor is an extrinsic semiconductor, which is obtained by doping the trivalent impurity atoms such as boron, gallium or indium, to the pure germanium or silicon semiconductor. The impurity atoms added create vacancies of electrons, or hole in the structure, and are called acceptor atoms. The holes are majority charges carriers, and electrons are minority charge carriers. Semiconductor. There are 3 types of materials used in electronic components. Electrical conductors are materials that allow electricity to flow through them easily. Electrical insulators are materials that prevent electrical flow. Semiconductor materials exhibit both conducting and insulating properties. The way in which the material is connected to a power supply determines whether it will conduct an electrical current or prevent it from flowing. A useful way to visualize the difference between conductors, insulators and semiconductors is to plot the available energies for electrons in the materials. Atoms of crystalline solids are closely packed as in crystal lattice, so that their energy levels are closely distributed as energy bands. Energy bands of crystalline solids are made up of the upper conduction band occupied by conduction electrons that are free to move between atoms as electric current. The lower valence band occupied by valence electrons that are tightly bound to their atoms and are not free to move about. In some metals, the conduction band and the valence band may overlap. Thus, the conduction band is occupied by many conduction electrons, causing these metals to become good conductors of electricity. In insulators, the conduction band and the valence band are separated by a band gap called the forbidden gap. For an insulating material, the valence band is completely filled with electrons, which are tightly bound to the atoms, but the conduction band is empty. The 2 energy bands are separated by a very wide forbidden gap. Therefore, the electrons are unable to gain enough energy to jump from the valence band to the conduction band. In semiconductor, the conduction band and the valence band are also separated by forbidden gap. For a semiconductor material, the forbidden gap is narrower compared to the insulating material. This enables some electrons with enough energy to jump from the valence band to the conduction band easily. At very low temperatures, the semiconductor behaves like an insulator, since there is no free electron in the conduction band. At higher temperatures, electrons excited by heat energy can gain enough energy to jump from the valence band to the conduction band. When this happens, the electron leave holes in the valence band. These holes behave like positive charge carriers, and can also move freely. When a potential difference is connected across a semiconductor, the holes and electrons move in opposite directions. Thus, both charge carriers contribute to the current that flows. As temperature rises, the electric conductivity of the semiconductor increases, caused by a larger number of electrons being excited into the conduction band, leaving a larger number of holes in the valence band.